is right now on or off?
Check. Check.
Okay, so let us start. Okay, welcome back. And in this session too, we'll have two talks. The first talk will be given by Professor Kausik Majumdar from IISc Bangalore. He'll be talking about Moire-trapped excitons and excitonic complexes.
Thank you. So this is an engineered 2D materials conference. So I'll discuss the kind of engineering that we are doing with this, these excitons and excitonic complexes in 2D materials. Specifically, so toward the end I might forget, so I'll just acknowledge upfront. I'm very fortunate to have an excellent group of students working with me, and also I thank my collaborators, Arun from IISc, and of course the Japanese group for the HBN that we use. So today, I'll talk about a couple of things. So one is these twisted heterobilars. I'm pretty sure you have been listening to multiple of these twistronic talks. So there's you don't have to introduce that in this conference. But what I'll focus on is in these heterojunction, if you have heterobilar, you have these interlayer excitons, and they are trapped in a Moire potential. So how can you engineer these trapped excitons, and not just excitons but also excitonic complexes, right? Higher order particles and all. Okay. So this is one platform that we are working on. So there is another platform that we are working on, which is these nanopillars. And you engineer the band structure of the 2D material. It's sort of a strain engineering, by putting these monolayers on these nanopillars. And what I'll show you that these give rise to beautiful single photon emission. And then so what I'll do is I'll kind of combine these two platforms and show you that this heterobilar, this Moire heterobilar, if you put it on these nanopillars, so basically you have this periodic array of Moire pockets, and that sort of is modulated with a much lower spatial frequency. So basically you have a strain well, and within that you have this higher frequency Moire pockets. Okay, and what happens to the excitons in that? So this is what my outline. So let me start with the excitons in these heterobilars. So I'm not introducing Moire here. I'm assuming that it's sort of multiple times in this conference you have been talked about. So there are these potential wells. And these potential wells, are actually for excitons here, is because, so I'm really talking about the change, the modulation in the band gap, of the material, more specifically the interlayer gap that changes in a periodic manner depending on the atomic registry, right? So specifically, we are talking about tungsten sulfide and tungsten selenide, this heterojunction. So this is a type 2 heterojunction. So the electron stays in tungsten sulfide and the hole stays in tungsten selenide. So this is the interlayer exciton. Obviously, this interlayer exciton has much lower oscillator strength compared to the typical intralayer exciton that we talk about individually in these materials, where the electron and the hole, they are staying in the same layer, right? Simply because the wave function overlap reduces because of the spatial gap, right? And also, so there are debates, but it's not guaranteed that they are also momentum direct. So there are multiple theories in that, but the bottom line is that this is going to be a much lower oscillator strength exciton, and which in some sense is good for experimentalists because it does give you enough time to measure them and manipulate them. Like for example, the radiative lifetime of the intralayer excitons, they can be on the order of a picosecond, while this I'll show you that it can go all the way up to 100 nanoseconds. It's almost like it's living forever for TMDs. Okay. So the device structure that we'll discuss is this. So it's a heterobilayer, and we have a gating arrangement here. The HPN is a gate dielectric. So that way, you should be able to dope the system. Okay. So there are two tuning parameters we'll talk about. So one is the gating modulation, and the second is the modulation by optical power. Okay. So the first thing is, so this is sort of a photoluminescence spectrum of some of these heterobilairs at the interlayer regime. So this is, you see around 1.4 electron volts. So I'll not be talking in terms of nanometers. I'll be talking in terms of electron volts. So this is like about 1.4 electron volt or so. Okay, and so you clearly see like signature of 3 different peaks, and they are equally separated, more or less equally separated. Okay, and this has been, of course, touted to be the harmonic potential well. So it's a 2D harmonic potential well, right? And so you expect that the states are equally separated, right? And this is sort of a signature of that. Now, so a couple of measurements. So one is, I told you, like there's a lifetime measurement. So the lowest energy is the X naught. We got tell that is X naught. The next one is X1, and the upper one is the X2. So these are the 3 excitonic features that we are able to observe. Beyond that, we are not able to observe. Okay. So of course, from the separation, you can sort of get an idea of what is the depth of the Moire well, right? Now, in terms of the lifetime, so the X naught, which is you see is almost like living forever. So this we could measure up to like a couple of hundreds of nanoseconds or so, but I believe it's living even longer than that. Okay, the next one is slightly lower lived, and so I'll give you the numbers later. And the topmost one is even shorter lived, and this makes sense because was there a question? Yes.
Yeah, just a quick question. So what is it about the X naught exciton that gives it that anomalously long lifetime?
Yeah, so right. So you see that so there are so this is the lowest energy level, and this is well protected in a Moire pocket. So the non-radiative lifetimes are much shorter for this particular exciton. However, this particular exciton, it can always come down to this one. So there is a lower energy level available here, and similarly for this one. So that's why progressively we believe that it's sort of becoming faster and faster, just because of the non-radiative lifetime. Nothing to do with the radiative lifetime as such. Okay. So I'll show some gating dependence of this modulation later, so that will make it even more clear. The other interesting effect here, what we observe is that the power loss. So let's say you increase the power and you observe the photoluminescence intensity. So typically, if you have a free exciton and there is, let's say, nothing else perturbing the system, the exciton intensity, if you just do a one-line math, it will come to be proportional to the power that you are introducing. right? So here, what you observe is that the topmost one, which is almost like p to the power 1, so that makes sense. However, the ones which are more protected, they are becoming p to the power 0.5, this p to the power 0.34. So it's becoming more and more like, such. You increase the power, you're not able to generate enough number of excitons. And this is again a very common feature for confined systems, just that there is a bottleneck for which you are not able to generate sufficient number of excitons. Okay, so that's nice. And because you have this nonlinear, rather different power laws, what will happen is that the spectral feature is going to be significantly different if you are increasing your power. So for example, at very low power, this is like 30 nanowatts of power, you see only X naught, a very strong feature of X naught, and then the next exciton level. However, if you increase the power a little bit more to like about a microwatt or so, then this guy is there, but the middle one, it actually increases more than that, and you start seeing the topmost one at a with a small intensity, and even higher power this guy increases even further. So you see that the spectral feature is going to be significantly dominated by the actual optical power that you are employing in the system. Okay, all right. So now let's come to the gate voltage tuning part. So what you observe is that as you increase the gate voltage, so this is the gate voltage value and this is the emission energy. So the negative energy voltage part, it really doesn't, anything really happens. And this negative energy means, this is sort of a, you're doping the system, p-type, or rather you're trying to introduce holes. And we know that, so what happens is the gate was sitting toward the WS2 side, and we know from our experience that it's very difficult to p-dope a WS2 or even MOS2 as a matter of fact. And because of that, this, it just probably depletes the system, nothing beyond happens, you are not really introducing, sufficient number of holes. However, when you are going to the n-doped regime, we know that you can very nicely dope this system, n-type. And so, one is that, the intensity of the excitons, all the excitons, they degrade very significantly. And also, you observe a slight, redshift. It's actually not slight. You see the scale bar here, so it's like, larger. So I'm kind of, plotting the shift over here. So you see that the bottommost one, there's an X naught, that moves pretty fast, about 15 millielectron volt per volt. Compared to that, this one, which is the middle one, which is about 7 millielectron volt per volt, and this is about 5 millielectron volt per volt. So the rate at which the shift is happening is fastest for the X naught. Now, this makes the system, significantly different. The reason is that because the shift is different, so they are no more equally separated. So this is no more a harmonic system. You are introducing anharmonicity to the system. So there is a harmonic to anharmonic, shift that you were talking about when you are introducing, this gate voltage. Okay. So that's one thing. I'll discuss about the anharmonicity part in the next slide. There is another thing which is very interesting, which is, the redshift is significantly dependent on the localization. If you go back to our previous slide, so this is the strongest localization, and this is the weakest localization. This guy doesn't see, because this is not an infinite harmonic well, right? It has a finite height. So so these does see a significant amount of delocalization. Okay. So, and this redshift, by the way, is pretty obvious, because the fact that, you are electron doping the system, so let's say with respect to the Fermi level, this conduction band edge, comes down, and so the spectral gap between this conduction band edge and this valence band edge of WSE2, that is reducing, and which is actually, giving rise to this doping induced redshift. Okay. All right. So now, so we did some, simple, electrostatic solution. So by solving the Poisson equation. So what we did is that, so this is, your XY dimensions. This is the Moire superlattice, and you are, let's say, introducing some gate voltage. So it's just a self-consistent solution. So at, let's say, let us say your Fermi level is somewhere here, and you start, doping this system. So what will happen is that this, conduction band will start moving down. So that's fine. So no problem. It's, just simply from your field effect transistor theory, it will kind of, come down in a linear manner. But the moment, this guy comes, close to the Fermi level, what will happen is that it will start introducing carriers. And the moment it starts introducing carriers, it will have, this screening, into effect. And if you look at it carefully, this edge will, come to closer to the, Fermi level earlier than this part. And what it means is that this portion will be screened more compared to the other portion. So in effect, what I'm really trying to say is that if you introduce more KDS in the system, your fluctuation is going to go down, and which is obvious. Like, for example, if I give you a metal, metal is a uniform unipotential system, right? It does not really have any potential fluctuation, right? However, you are not really changing the band gap of the system, so effectively, this extra, lack of, fluctuation that gets translated into the valence band. So eventually, what happens is that your electron becomes, more delocalized, while the hole becomes, more strongly localized. So what's the signature of this? So if you look at it again, the potential fluctuation, so the maximum you will see, when this is kind of hitting this, right? So it's the center of the, the Moire pocket. So right here, you will have maximum, perturbation, and away from it, you have minimum perturbation. Now, if you look at the, the psi or the mod, the wave function of the mod psi squared of psi of x naught, that's sort of, centrally picked, while of x1, it sort of, have two lobes with, nodes. So if I just do a simple, qualitative, perturbation calculation, obviously, this guy, will have, maximum perturbation, while this overlap is minimum with the green one, which is the psi one, so that will go to 0. So eventually, what I'm saying is that this guy, which is x naught, it will see a linear Stark shift. While the linear Stark shift is almost 0 for this one, but it will actually see a quadratic Stark shift. So those who have worked on this, Stark shift, that typically in a quantum well, the quantum confined Stark shift, that is, you don't typically observe the linear Stark shift. You first observe the quadratic Stark shift, and that's because your potential is, linear there. You apply a constant electric field. But here, just because of a vertical electric field, we are able to obtain a sort of a, even function of the potential delta V. And so we don't observe, quadratic Stark shift for the first one. We observe directly a linear Stark shift, which is an exciting news because it can be stronger. On the other hand, this guy is actually 0, but so it actually starts showing the second order Stark shift. Okay, so that is something in contradiction with typical quantum confined Stark effect. All right. So the other thing that we felt was interesting is with the application of a gate voltage, you can dramatically change the lifetime. So this is the result. For example, this is the x naught. So I told you, right? Initially it was, let's say, about 100 nanosecond or so. You increase your gate voltage. I'm sorry, this didn't come out well. This is the gate voltage. So as you increase the gate voltage, it dramatically comes down all the way to like maybe a couple of nanoseconds or so. If you increase it further, it will just after this actually you cannot see the exciton feature at all. Okay, and that's because we can see this all the way up to 100 nanoseconds simply because, as I said, that the non-radiative process is much less here. But here for these two excitons, so already there is a strong non-radiative process, and you start with this, and so they do go down with gate voltage also. But of course, you don't see here, because it's like an extra, constant factor is over here. That's already there, right? But nonetheless, you can change this, lifetime numbers very beautifully, with gate voltage. So that's from an engineer's point of view, that's very interesting. Okay. All right. So now, I'll just switch gears a little bit, and I'll discuss about, this nanopillars and what's the role of, having strain in this. So this is another platform that we are working on. So, and this we are talking in the context of single photon emission. So again, single photon emission, as you may be well aware of, that it's very important as far as quantum technology is concerned, and so this is sort of useful in many applications, like quantum communication, quantum computing, quantum networks like QKD networks and all, quantum sensing. So all these, so you are basically embedding or encoding the information in a single photon. It could be in the polarization of single photon or something else, but single photon by itself is required, and which is why single photon emitter and single photon detector both are very important technologies, and so our group is working on both these technologies very aggressively. So of course quantum simulation as well. Yeah. So just to it might for this audience it might not be new, so I will just quickly introduce you. So there is so what is a good benchmarking here? So it's a maximum photon emission rate. You need to get these photons one by one. It's like instead of multiple cars running in a street, you need sort of a single one lane, and cars should go like one by one. So that's a requirement. But you must also have a very high rate of emission. Otherwise you cannot encode the information at a fast rate. So also there is a parameter which is the single photon purity. We measure it through second order correlation, and it should be ideally 0. So basically this is a good corner. This is a bad corner, right? So we'd like to have our devices working in this corner. And if we look at the typical reports that are already there, you see that you try to sort of improve the purity. That is, you try to reduce G to 0. What happens is that your rate often goes down, right? And that's something which we would like to avoid, right? So yeah. So also very high rates are typically not observed, and that's something we were interested to work on. And so for that, this is an interesting platform where you have these nanopillars, and you put a single monolayer of some material. So here for some material we put tungsten selenide. Okay. So what really happens is that because you are introducing a strain in this pillar region, there is a band gap reduction in the monolayer. And because you are introducing a reduction in band gap, if you excite through laser, these excitons, they will eventually funnel, because this is the lower energy state. Okay. And now, so let's say there is a point defect. So now and it is very likely that the point defect is at the top of the pillar. This comes from our experience, from our measured results and all. Invariably there will be some point defect over here, because you are putting the strain here, and on top of that there could be multiple point defects. They are usually spectrally separate. That helps us in getting different single photon emitters which you can separate out spectrally. And so what happens is that because there are a lot of excitons here, they act like a reservoir here, and it kind of falls here, and this is a single state. So that will emit one photon, the next one comes here, that will emit photons, like that. So that's how, through this bottleneck single level state, you can get one photon at a time. Okay. And we did a bunch of calculations which I am not showing here, but so there is another problem here, by the way. So it's good to have a lot of excitons here, because it acts like a reservoir, and your reservoir ideally should be an infinite supplier, right? But the fact that you are forcing many excitons to come close by, there is a very strong exciton annihilation that happens, and this is just the Auger process, right? And because of that, you tend to reduce this, exciton density right on top of the pillar, and that's a bad thing.
Question.
Yes.
Somehow it seems that like single photon detection should be related in some way to single photon emission. But if I play your movie backwards, I don't see how that.
Could you come again? Sorry.
Yeah, I'm just thinking, in physics, there's a lot of reciprocal relations. So it seems that somehow, based on analogy to many other physics situations, that's, an efficient single photon emitter should be able to be run backwards or something as some efficient single photon detector, but I don't see how it would work.
It unfortunately doesn't work from an engineering point of view, because you need to have, for a detector point of view, you need to have a good collection. So a point cannot be a good detector just because it does not have enough cross section to collect those photons. This is just an engineering point of view. It just doesn't work, So if you look at the detectors that are available in market, you'd get like 500 micrometer kind of, and even bigger than that. So they are highly attractive and costlier also. Simply because you don't want to miss out on any of the photons that are coming to your system. Now, if I just have a point defect and I force my photon to go and interact there, it's very, very difficult job. Unless you have some sort of a big aperture where you collect and force that to go to the defect. If you can do that, yes, that's a great thing. But otherwise, it's going to be a little tricky. Yeah.
Okay, so is a summary of what you're saying that the engineering aspect of photon detection is entirely different than the engineering aspect?
Yes, absolutely. Yes.
Production.
Yes. So there are multiple ways of detecting single photons, which unfortunately I will not be covering today, but we can take it offline and discuss. There are very interesting aspects of single photon detection. Yes. Okay. So so we did this sort of a rate equation kind of thing. It's a nonlinear because Auger is like n squared term, right? So so Auger strength and the strain in the system. So you need more strain. That way you can funnel more excitons. But at the same time, more excitons means more Auger. So is there a sort of an optimum situation or something? So what the simulation told us is that you increase strain, that actually is going to help you. Okay. So we would like to say, however, at the same time, if you can reduce Auger, through some other mechanism, that's also going to be very useful. Okay, so we would prefer to have in this high strain regime. So let us see how we try to do that. So what we do is that we just increase this height of the pillar. So if you increase the height of the pillar, then so you are basically increasing strain. So that's one thing we'll do. So what we are basically proposing is that you increase the height of the pillar, the rate at which your single photons are going to come out are going to be is going to be more. Okay, and this okay, so that's one thing we do. So we use about a 3:1 ratio. This is if we look at the results from the literature, this is the highest pillar aspect ratio that we have used. I think before this the best number was like something like about I don't remember exactly, like 2:1 or something. Okay. Okay, so that's a good question. So I'll just talk about that next. Yeah. So maybe I'll start with that only. So the pillar, so even if you look at literature and all, often you see that these pillars are like silicon pillars or silicon dioxide pillars, and they are very hard. And the problem of these hard pillars is that you are talking about a very tall pillar, and you put this monolayer. Often they punch through, and if you actually punch through, it becomes a mess, and you don't really see they're like too many defects. You don't want too many defects. You need to be at some optimum point, right? So they just don't work. And so what we do is that instead of that, we use a photoresist, and this is a negative photoresist, and we bake it, and that gives it enough mechanical strength, and at the same time it's so-called soft enough that it doesn't punch through. So our yield was pretty good. I'll show you some data after this. So this is sort of working well. Okay. I'll show you the spectral one. So these are, well, I do not have sort of an answer to what kind of structure we're talking about, but I'm pretty sure these are all like point defects about 200 MeV below the exciton gap. So these are not mid gap, but somewhere around 200 MeV below the exciton gap. Yeah, so that's. So the other point I would like to mention here is that we put a gold over here. The reason why we put this gold is because so this is sort of a mono layer, and if you excite with laser, every part will start emitting, and that's something we don't want. We want only this part to be emitting. So if we put gold, so you basically quench all the excitons which are somewhere here. Okay, and that actually helps us a lot. I'll show you in the next slide. And also this gold helps us to sort of reflect the light back, so it's easier to have your sort of coupling in an objective. Okay, so these are about 100 nanometers. So this is the yield I was talking about. See, so these are all the pillars, and almost maybe apart from couple of them, almost all of them are bright. So that is very nice because the yield is good, and also in between pillars this is like completely dark, and that's because of the gold. Gold is just eating up all the excitons, right? So this is really helping us to get higher purity of single photons. Okay, so these are the spectral features that I was talking about. So you see, the exciton, which you hardly see, this is the free exciton. It's about 1.75 electron volt at low temperature. And this is, by the way, like 4 Kelvin or so measurement. And these are the sharp peaks that I'm talking about. So this is about 200 MeV below this. Okay, and these are like different pillars. So more or less they emit in the range of 800 to like 775, and this is very important because the satellite quantum communication is around 800 nanometer. So that way, it has this practical application. Okay, so this is the lifetime number. So this is about 500 picoseconds or so is the lifetime. This is like much longer lived because it is not coming from the free exciton. It's from a confined exciton inside the defect. It is actually, so if you do everything right, and this is the radiative lifetime, it shows that ideally you should be able to go to like a 2 gigahertz kind of numbers. Of course, no one does, and which tells us that this is really not the fully radiative lifetime. It does have significant non-radiative component into it. This is the second order, the intensity correlation measurement. So for those who are new to this, anything below 0.5, it tells it quantum mechanically, it confirms that this is a single photon. Okay, and so the number that we got is about 0.11. There was one more measurement which showed like 0.03 or something, if I remember it correctly. So this sort of tells you that it is a highly pure single photon emission. Okay. Yeah, and by the way, this is measured at 1 megahertz rate, which is so pretty good. And the maximum saturation count that we could achieve is about 10 mega counts per second, like 10 megahertz. So 10 megahertz, we are actually collecting. So what it means is that, so this is the collected rate, by the way. If you have a dipole, it kind of emits in multiple directions, which I'll show you here. So this is kind of the simulated emission pattern. You see that the gold almost blocks emission from the backside. So most of the light you are able to collect on top. And of course there are some surface waves and all. Our objective collects within about 30 degrees or so. So within this we are collecting so this is about 1/3 of the total emission. So 10 megahertz means the total emission rate is about 30 megahertz or so, which is pretty good. And also these are highly polarized emissions that depends on the structure of the defect. So again, this is also very important to get this, this HOM type measurements where you want to prove that these photons are really indistinguishable in nature. Okay. All right. So So yeah, so if we just see our data kind of is here, which is something we were quite excited about, and of course we are working on this more and to get it even better and better. Okay, all right. So just coming back to today's topic, so these two independent platforms we developed in the lab, and now we wanted to see, okay, what happens if I transfer this this heterobilayer on these pillars, because a pillar by itself is creating a strain well, and within that we'll have this tiny Moire pocket. So what happens? What is the excitonic feature here? So the first thing, so I'll probably, this is a work in progress, so I'll probably just give you the results without a lot of explanations. The first thing is that the second harmonic generation, this SHG has a beautiful signal here. They're very strong, on the pillars. The other portions are gold. This is like, almost quenched. So this maps out, the entire flake in SHG, very nicely. This is, thanks to my colleague Arun, in whose lab, we have done this measurement. So this is, one interesting feature, and this is something which is, I guess, open for discussion, how this kind of, strong emission that happens, a strong SHG signal that comes out, from this heterobilayer, which is highly strained. Okay. Of course, there is an inversion symmetry breaking, but beyond that, if there is something else is happening, something which is worth looking at. Second thing is that, so we talked about the funneling. So it's not just a change in the band gap, but it's also, again, if we look at, I mean, I've not done these calculations, but there are reports from DFT calculations which show that it's the conduction band that actually bends. The valence band more or less remains flat. So what it means is that if you excite with, let's say an off-resonant laser, there is a lot of electrons which will also, funnel not much of the holes. So excitons will funnel because there is a change in the band gap, and electrons will also funnel. So you are actually doping this top of the pillars. And the proof is this. So this is a mapping of the trion to exciton, and we see a very strong, trion to exciton mappings. So those again who are working in the field, they know that these trions, or rather the fermipolarons, they are a signature of strong doping in the system. Okay, and on top of the pillar, it's invariably getting strong this fermipolaron peaks, and what it means is that you are very likely doping this, and this doping simply happens as I said because the electrons are actually funneling into this top of the pillars. The other thing is that of course pillar to pillar there is a variation in the strain, which is why you see that there is a sort of a redshift, or strain does redshift it. Also, we believe that because you are doping it, and if you have more strain, then you will be doping the system more, and if you dope the system more, because this guy will come down, this interlayer gap will also reduce, and it will have a redshift. So this is also another sort of proof that there is a strong doping that's happening because it's a function of the strain. Okay. All right. So what happens with optical power? Now, so there are a couple of very interesting things here. So one is these peaks. So at very low power, I see only this peak, and this is what we call as excitons. These are like two different samples. The separations are different because the twist angle was different. So that's one thing. But at very low power, you see a single peak, very weak features of the other peaks. Now, as you increase your power, there are a couple of peaks that start, appearing, both these cases, and also there is something, that start appearing on the right side as well, right? So this is again, very interesting. I'll tell you why this is very interesting. But before that, if I just look at a single peak, there's really not much of a movement. if I compare this with the flat, Moire sample, if you increase your power, because of this dipolar repulsion, by the way, the dipolar repulsion is very, very strong in these, Moire samples, the heterobilars, because the electrons are in one layer and the holes are in another layer. So this electron-hole attraction, they are like, diagonal, but electron, hole, they are in the same layer. So the entire dipole will start repelling. And because of the repulsion, what we normally observe is that you increase your power, you see a strong, blue shift of the, and we don't see anything like that. And I guess the answer is pretty obvious because I told you, as you increase your power, your electron doping also, apart from the dipolar repulsion, so they basically tend to cancel each other. Okay. So that's a thing. I think I'm okay. I've just 1 minute. So this 1 minute is for 40 minutes, right? Okay, cool. So so another thing is that then this lifetimes are these are like much faster. This is nowhere close to 100 nanoseconds or so. There's something like 1 nanosecond or even less. Even there is a faster components over here also. So they are like maybe 100 picosecond or something, and so which also makes sense because there are these lower energy states available here. So so it's going to a lot of non-radiative processes. Okay, so I'll end with so this is for my last but one slide. So what we observe, and this is something we are very intrigued, is that the exciton shows a power law close to like 1.78. It's just not possible in a normal situation. Exciton has to be p to the power 1, right? We see p to the power 1.78, almost like p squared. And this is something so what we believe, and this is based on again some calculations that we did, is that so when you have this pillar and you're forcing a lot of these interlayer, like these excitons, they're coming close to each other, they have a very strong dipolar repulsion. And because of the dipolar repulsion, there is a blue shift that's happening. And if you do the calculation, it turns out that so because of the it just becomes more flatter and flatter. So the size, the diameter of the pillar is actually increasing just with power. It's a dynamic variation of the pillar diameter in some way, right? However, you don't see this blue shift though, because I told you that there is this electron doping, which is kind of red shifting, is just cancelling each other. But nonetheless, the pillar diameter is actually increasing, and so you are actually covering more and more Moire pockets. It will actually is an area, right? It will go as a square, and that's why this close to 2 is coming. So if you kind of model from this, and we were able to actually get a very nice fit to this. So you can see that so initially these are the Moire pockets. Now when they get flatter, you are actually all these so earlier, for example, this guy was not contributing that much, but now because it is flatter, this guy is also eating up the excitons and they are emitting. So you get a superlinear power law. And so I'll probably stop here. So we see this biexcitonic features also. With power, it's like p to the power 3. If we plot with respect to exciton, this is like 1.68, which is very interesting. This is what we are really saying is that this is the low, like the red side of the exciton, which is interesting because to that, what people believe is that it's very difficult to stabilize a biexciton in a Moire pocket simply because of this Coulombic repulsions. Okay. But what we are observing here is that there is a biexciton feature, very clear feature because of with exciton it goes as 1.68, and that is actually getting stabilized within the same Moire pocket. And we believe this is happening because of one is because of the exchange interaction, and second thing is because of an attraction between these two layers. So this is again, like I said, a work in progress. We'll probably, next time we meet, we'll, talk more detailed about this. But this is interesting because, just a few months back, there was a paper from Sarong's group which shows that this, these biexcitons, they're actually on the blue side of it. It's not really on the red side. So that becomes, a very interesting thing now because, that's not really a true biexciton, but you're forced to keep the two excitons in the same Moire pocket, but here they are actually stabilized. You don't need any extra force from the Moire pocket. So we'll see what happens, to that. So with that, I'll probably close. So I just showed you that is heterobilayer, interlayer mod excitons. They are like highly tunable with optical power and gate voltage. And this nanopillar, that's an interesting platform, for the single photon emission. And these two things you can combine to get, beautiful, mod excitonic features. Thank you.
So, thanks. We already had some couple of questions, but we can more. Yeah,
Yes.
we can.